Let's work on example 12.16 here. I have a manufacturing facility that produces aluminum cans. The design calls for a radius of 1 inch and a height of 5 inches, but due to some mismanagement of the machinery, we're producing a can that's a little bit off of those measurements, a radius of 1.03 and a height of 4.9. Estimate the change in the volume using the total differential. So we don't actually have to find the total differential in order to find the change in the volume. Right, the change in the volume is actually the second part, where I just need to evaluate the volume at the new points. So when my radius is 1.03 and my height is 4.9, and I need to subtract the volume at what they're supposed to be. Right, this would be the actual change in the volume. But the idea here is that I can estimate the change in the volume by traveling along the tangent plane of this function. So the change in the volume is approximately equal to dV, which is the differential. It will be the gradient of the volume at our initial point dotted with R minus R naught, H minus H naught. Oops, that's a vector. Right, which effectively just boils down to the partial derivative of the volume equation in the R direction at a certain point times R minus R naught plus the partial derivative of the volume equation in the H direction at a certain point times H minus H naught. Right, this is the exact same thing in one dimension. If you have a function and you're traveling along a tangent line, then the change in the y values is given to you by the slope of this function, f prime of x, times the distance that you traveled. Right, except now we have multiple derivatives. So we can travel in multiple directions. So it's the change in the r direction times how far you moved in the r direction, and it's the change in the height direction times how far you moved in the height direction. All right, so we do not have the volume equations yet. It is a cylindrical can, so the volume is going to be pi r squared times h. So the partial derivative of the volume is going to be 2 pi r h. And I want to evaluate this at r naught, h naught. I'm then going to multiply by r minus r naught. The partial derivative of the volume equation in the h direction is pi r squared, which we will multiply by h minus h naught. Okay. So what to choose as r naught and h naught? I'm going to assume that because the can is supposed to have a radius of 1 inch and a height of 5, that's where we're going to center our tangent line, and then we're going to use the other point as the point that we're actually at. So let's think about this here. The partial derivative of the volume equation with respect to radius at the point when your radius is 1 and your height is 5 is going to be 2 pi r h. So that gives you the rate of change of the volume in the r direction, and your r is moving from 1 to 1.03. We will add to that pi r squared evaluated when r is equal to 1, because that's the rate of change of the volume equation in the height direction. And how far did we move in the height direction? We're getting cans that are 4.9s, but we were expecting cans that were 5s. So running through this, we end up at 10 pi times 0.03 plus pi times minus 0.1. All right, so let's get rid of these pi's and make an approximation. This is about 0.6283, and everything was measured in inches. So this is a volume, it's going to be measured in inches cubed. So due to the miscalibration of the machinery, we're making cans that increased volume by about 0.6283 cubic inches. Now, let's actually find the real change in the volume. The real change in the volume is the volume that we're getting right now minus the volume that we were supposed to get or that we started at. So if you evaluate your volume at 1.03 and a height of 4.9, you get 16.331 cubic inches. And if you subtract the volume that you're supposed to get, you get 15.708 cubic inches. So this was an approximation. So the actual change in the volume is 0.623 cubic inches. That's not far off from our approximation.